In the world of fluid mechanics, my group will be covering Chapter 12, Turbo Machines. Turbo machines are machines that use blades attached to a rotor to remove or produce energy from a flow. A common example of a turbo machine is a centrifugal pump that is used to pump water and is often found in leaf blowers. Centrifugal pumps do work on the fluid, often increasing fluid velocity. Another typical example of a turbo machine is a turbine. As shown below, these are often used with wind or steam to produce power. Unlike pumps that do work on the fluid, fluids do work on turbines to produce energy. There are three types of classifications for turbo machines. Radial flow machines consist of a significant radial flow component at the rotor's inlet, exit, or both the inlet and exit. This means that the fluid flows across the radii of rotation of the blades and is perpendicular to the axis of rotation. An axial flow machine contains a significant axial flow component at the inlet or outlet of the rotor. This means that the fluid flow is parallel to the pump shaft. The third type of turbo machine is a mixed flow machine. This is a combination of both a radial and an axial flow machine. For the work transfer of a turbo machine, we define it using the equation V equals W plus U, where we define U as the blade speed, which can be calculated using omega times R, where omega is the angular velocity and R is the radius from the axis of the fan. V is the absolute fluid velocity, which can be thought of as the velocity seen by a spectator watching the fan, and W is the relative velocity, which can be thought of as the speed seen from the perspective of the fan blade. Next, we will talk about angular momentum in turbo machines. Work is defined as a force times a distance, but it can also be considered torque times angular displacement. If the work is positive, meaning the shaft torque and rotation of the rotor are in the same direction, it is a pump. If the shaft torque and rotation of the rotor are in opposite directions, meaning work is negative, it is a turbine. At the bottom of this slide is what is commonly referred to as the Euler turbo machine equations. In the first equation, we can see that the shaft torque is equal to the mass flow rate in times the radius times the angular component of velocity plus the mass flow rate out times the radius times the angular velocity component out. We can then set it equal to the second equation, and knowing that U equals omega times R, to obtain the third equation for shaft work. If we are at steady state, we can get the shaft work per unit mass by factoring out m dot and dividing by it to obtain the fourth equation. The fifth equation is a much more tedious derivation, but it is important to note that this equation allows you to calculate the shaft torque per unit mass given the absolute fluid speed, the fluid speed relative to the blade, and the speed of the blade.
Hi, Josh Grunden here, and now we're going to cover our first turbo machine, the centrifugal pump. Our centrifugal pumps are low capacity and high head pumps. This means that they have a low flow rate, but result in a large energy change in the fluid, mainly in the form of pressure. The centrifugal pump is our most common radial flow turbo machine. It comes with our patented impeller and casing. The pump functions by the impeller rotating and sucking fluid through the eye of the casing so that the fluid flows radially outward. The rotating blades of the impeller add energy to the fluid, resulting in an increase in pressure and velocity as the fluid flows towards the periphery of the blade, where it is discharged into the volute casing. Once in the volute casing, the velocity of the fluid is reduced, corresponding to another increase in fluid pressure, and a uniform velocity distribution is discharged out of the pump. We have two different impellers to offer. We have our traditional open impeller, and if that doesn't suit you, then we have the enclosed impeller. The open impeller is faster, easier to clean and repair, and optimal for smaller pumps. The enclosed impeller is strong, more difficult to clean and repair, and optimal for larger pumps. Our impellers also come as single or double suction. Our double suction impellers reduce thrust on the shaft, making them more durable, and have a larger inlet flow area such that it reduces inlet velocities. We have three blade options for your impeller needs. The first is the traditional backward curved blades with a blade angle less than 90 degrees. The second are our radial blades with blade angle equal to 90 degrees. These are traditionally used for small and inexpensive pumps. The third are forward curved blades with blade angle greater than 90 degrees. These may result in unstable flow, however, which can damage the pump and thus are not often used in pump design. Our pumps are designed to prevent cavitation. Cavitation is when the liquid pressure at a location is reduced to the vapor pressure of the liquid and bubbles form. Cavitation is most likely to occur at the impeller eye, as that is the spot in the pump where pressure is the lowest. This can damage the impeller and pump and result in a loss of efficiency. To prevent this, the actual net positive suction head must always exceed the required net positive suction head. Another warning is to not operate the centrifugal pump with the discharge valve closed, as temperature and mechanical stress will build up and extensive damage to the pump may be warranted. But wait, there's more. Why have only one pump when you can have multiple, so that you can use your pumps in series or parallel? In series, your pump heads add so that the overall discharge pressure is higher. Arranging your pumps in parallel adds the fluid to the pumps together, so the fluid flows out of the system at a faster rate. We're not done yet. If our traditional size pump does not suit your needs, we have scaling to construct the pump of your dreams. We offer you two scaling options, changing the operating speed of the pump or the impeller diameter. The relations between changing the operating speed and impeller diameter on flow, head, and power of the pump can be seen here. By knowing the flow, head, and power that you wish the pump to achieve, pumps can be scaled appropriately to meet your desires.
We've talked a lot about centrifugal or radial flow pumps and their analysis. Now we're going to touch on axial flow pumps. Axial flow pumps are used for scenarios requiring high specific speeds and high flow rates at low heads, such as plumbing, drainage, and irrigation. Axial pumps are essentially a spinning propeller within a cylinder, and most of their flow is created by the tangential force of their spinning blades sucking up the fluid. This is a diagram of a vertical axial pump where the rotors are attached to a shaft which is powered by a motor. These spinning blades suck water in through the inlet, which is then guided upwards by the fixed stator blades. Some of these axial pumps can have multiple of these spinning blades, and some can have multiple of the fixed blades. It all depends on the type of the pump you use. Now we're going to touch on centrifugal versus axial pumps. The overarching concepts and definitions of analysis are applicable to both. However, due to the differing nature of how these pumps work, the characteristics of their flow are very different. Centrifugal pumps often have lower specific speeds, being less than 4,000, as opposed to axial pumps, which tend to have higher speeds, being over 9,000. When situations call for specific speeds in between these, mixed flow pumps have been developed to run efficiently at this intermediate range between 4,000 and 9,000. Mixed flow pumps, as the name implies, have both axial and centrifugal components in them. This is a chart showing differences in data between centrifugal, mixed, and axial pumps, all having the same flow rate. Looking at the chart, we see that as we transition from centrifugal to mixed to axial, we see that specific speed and RPM increases, but head and impeller diameter decreases. When the fluid you're transporting is some sort of gas or vapor, you're going to want to use a fan instead of a pump. Fans come in a very wide array of designs and sizes. Even relatively lightweight fans with low rotational speeds are able to transport large volumes of gas rather efficiently. Just like pumps, fan designs include radial flow fans, axial flow fans, as well as mixed flow fans, and their analysis is fairly similar to that of pumps, simply using different data terms such as pressure rise instead of head rise. Most fan analysis takes place under the incompressible assumption, or constant density. This is because the change in density for gas flowing through a fan system isn't normally enough to be considered impactful in the system.
Turbines are used to take energy from a flowing fluid. A torque is created from the interaction of the rotor and the flowing fluid. The torque is in the direction across the axis of spin angular velocity that is produced by the flow of fluid, as seen in the schematic below. An example of an industrial turbine is seen on the left. There are two types of turbines, the impulse turbine and the reaction turbine. Each is commonly used. The main difference between the turbines is how the rotor works. In an impulse turbine, the stream strikes the moving blades. For the reaction turbine, the stream flows through a guiding mechanism, then strikes the blades. The guiding mechanism makes the flow strike the blades with a change in pressure, while the impulse turbine operates isobarically. The change in pressure leads to a degree of reaction, which is a ratio between the enthalpy across the moving blade and the enthalpy across the nozzle and the moving blade. For the Pelton wheel, V theta 1 and V theta 2 can be described by the governing equations below. V theta 2 minus V theta 1, or the change in V theta, can be described as T shaft. To obtain the shaft work, of an impulse turbine, the change in V theta can be multiplied by the angular velocity. The efficiency and power of specific speed for both turbines can be described in the equations below. Power of specific speed can describe whether axial or radial will be more efficient. Efficiency can be simplified to the equation absolute value of actual work over reversible work. However, if the actual and reversible works are unknown or unobtainable, the equation below can be used to calculate efficiency. But typically, calculating actual and reversible work will be much easier. Here are our external pictorial references. And here is the reference for the textbook used.